13. So I'm going to kind of skip around a little bit here. So we're going to talk about solutions, and you already know about solutions. Solutions are anything that's aqueous, right? So aqueous. And it doesn't always have to be water. So this is a solution where water is the solvent. So there are two parts to a solution, the solute and the solvent. The solute is getting dissolved. And it's the lesser of the two. And the solvent is doing the dissolving. So when water is the solvent, we call it aqueous. It's the greater amount. So you can tell just by kind of looking at the amounts of stuff, which is your solute and which is your solvent. If you have a lot of water, a little bit of table salt, the table salt's the solute and the water's the solvent. You probably don't have like a lot of salt and a little bit of water in a situation like that. So mostly your solvent is going to be the thing that's in the most amount. It is a homogeneous mixture, so hopefully that rings a bell to something that is mixed thoroughly, doesn't have any floaty bits or different parts to it. It's just kind of all the same. We call water the universal solvent. Because it dissolves a lot of stuff. Because it dissolves a lot of things. Mostly like it dissolves a lot of ionic compounds because of its polarity. It can dissolve a lot of stuff. So just a few terms for solutions. So some common solvents that you might use in your chemistry careers, polar solvents, again, water is called the universal solvent. And non-polar solvents. You will use a lot of diethyl ether in organic chemistry. You actually use a lot of acetone in organic chemistry because it's a little more polar or non-polar than water. So you get a spectrum of this polarity. So like really polar, a little polar, really non-polar. And it kind of depends on what you're doing, what reaction you're doing, or what substance you want to dissolve, what solvent you use. So if I want to dissolve something non-polar, I have to use a non-polar solvent. If I wanted to dissolve something polar or mildly polar, I would use a solvent that looks kind of like that substance as far as like its polarity level. So that's why we say like dissolves like. So you've seen this before, but it really just means like if you want to dissolve something, you pick the solvent that looks the most like it or has the same kind of polarity or has the same kind of intermolecular forces, and they can interact with each other. You don't have to memorize this. This is just a table in your textbook of common solvents so you can see that maybe, you know, as you move forward, you remember, oh yeah, that's a solvent that is commonly used. So what is happening when something dissolves? So when something dissolves, you are forming an attraction between the solvent and the solute. So the solvent here in this image is water. That's the red and white thing that looks kind of like a Mickey Mouse. We got our oxygen here, and you have your hydrogens up here. And you notice that your oxygen is more negative. So it has this partial negative charge. And the partial negative of the oxygen is attracted to the positive of the sodium. And the positive of the hydrogen in water is attracted to the negative of the chloride. This interaction here is really strong. So it breaks the sodium chloride apart. So this is a hydrogen bond between two waters, right? Y'all should know that. This is an ion dipole. It's stronger. Okay, and the solute-solute attraction is kind of an ionic interaction here. I can say ionic attraction. So we're not like melting it, we're dissolving it. So the sodium and the chloride are still going to have attractive feelings toward each other. but they are going to be, you can separate them with the water. So these attractions have the solvent-solute attraction, so between water and sodium ion, for example, has to be greater than the attraction between the sodium chloride and the water to itself, or it won't separate, right? So like if the sodium and the chloride are too attracted to each other, the water cannot break them up. That's what happens when you get a precipitate. So the cation and the anion, they like each other a lot, and the water can't separate them. Okay, you can't break their hearts. You can't separate that love. So if you have a solid that has ions in it, this is how the water is going to kind of break them apart. It's kind of violent. The water kind of bashes into the ionic compound and it rips the ions apart and surrounds them so they can't get back together. And the higher your temperature of water, the faster those water particles are moving, the faster they're going to hit those ionic compounds, which is why you typically find if you have hot water, you can dissolve stuff faster and better, right? So if I want to dissolve sugar in water, hot water does that a lot better than cold water because the water particles are just moving faster and it can break apart that solid a lot faster. But do notice that all of your negative and positives are kind of moved around each other. So all the negative parts of water are surrounding the positive cation, and all the positive parts of water are surrounding the negative anion. So you may, at some point in your chemistry career, be asked to draw something like this. Like, hey, I'm going to have an ionic compound. How is water going to separate it? Like, what does the dissolving look like of this? So I want to introduce a term really quick, dissociation. If something dissolves into ions, we call that dissociation. So we are associated together and then we are dissociated, we separate. Or if something does not have ions, it just dissolves. So dissolves just means water is breaking that substance apart. Dissociation is a special type of dissolving that makes ions. So ionic compounds and acidic compounds can dissociate. Covalent compounds cannot dissociate because they do not have ions, so they will not make ions. Acids, when they break up in water, will make ions, and ionic compounds obviously will make ions. But covalent compounds will not dissociate. They can dissolve, but they cannot dissociate. Can dissolve as molecules, not as ions. So do not dissociate. So for example, I just want to make a quick note that if I give you CO2, like what makes that up? It's carbon and oxygen. It's not carbon 4+ and oxide 2-. That's not what this is. It's not an ionic compound here. This is a covalent compound because it's two nonmetals. So don't think about breaking covalent compounds into ions ever, ever, ever. Only ionic compounds and acidic compounds can you break into ions. And I do see this happening sometimes, and so I just want to clarify that. Questions about how things dissolve? And a lot of this is kind of like I know how things dissolve because I like put salt in water, so like I understand that, but. So again, kind of here's a picture of that, of the sodium ion. So sodium is separated from chloride. Y'all know this because we talked about complete and net ionic, right? So every time you have a complete a molecular equation and we break that equation into complete ionic, we break down everything that's aqueous. That's just the real life of what aqueous means. So you're just kind of breaking it apart, that's separating it into what it really looks like. It's a better model. So another term that we have used before is solubility. So you've used the solubility table on the back of your periodic tables. And solubility, though, is the amount of a compound that you can put in a certain amount of a liquid. So at a certain temperature. So the solubility of sodium chloride, if the water is at 25 degrees C, is 36 grams of sodium chloride per 100 grams of water. That per means a conversion factor. So you can use this. You could say 36 grams of sodium chloride equals 100 grams of water. And so I could use that as a conversion factor 100% at that temperature. As the temperature of the water increases, do you think that I can dissolve more or less sodium chloride? So if I were to increase the temperature of the water, do you think that would dissolve more or less? It would dissolve more, because the faster the particles are moving, the easier the water is at breaking apart. Think about water as like chiseling away at that ionic compound. So the faster the water molecules are moving, the more energy they have, the easier they're going to be chiseling away and moving around the beaker really fast and separating faster. So they're going to dissolve more. So faster, so higher temp. For solids, I'll say for solid compounds, solids and liquids. Equals higher solubility, meaning more grams in the water. Okay. This is typical, not all the time, but typical. That's one way that you increase the speed of dissolving, right? To make the water hot. Like if you're trying to dissolve sugar in cold water, it doesn't work. But if you heat the water up like in hot tea, it dissolves a lot faster. We'll talk about reaction rates a little bit more in chapter 15. So we can talk about solubility in solutions in terms of saturation. So saturation, if you've done any work in like photography on the computer or anything, you've noticed that there's probably a button that's like called color saturation. So if you have something at high color saturation, that means there's a lot of color, a lot of pigment in that area. Fully saturated means that as much as you can hold. Unsaturated would be, well, that's, you know, a lighter amount of pigment in that area. So saturated means that at that temperature, you've maxed out as much as you can put in. Okay, so I have as many particles of sodium chloride as I can get in that amount of water. If I put in any more, it won't get dissolved. So you can do this at your house. So take a cup of water, maybe in a see-through cup or a glass container or something, and sprinkle some salt in slowly, kind of mix it around until you get to a point where you're sprinkling the salt in and you see the salt particles just sink to the bottom. They don't dissolve anymore. You have reached the point of saturation when that happens. And for sodium chloride, it actually is not it is very soluble, but it's not as soluble as we think. A lot of other ionic compounds are more soluble than sodium chloride, meaning you can fit more in to water. So you can try that at home to kind of make a saturated solution of sodium chloride. You would sprinkle in some salt until you see it start coming out at the bottom where it's not dissolving anymore. That means your solution is saturated. The water says, I know you're putting in more, but I can't hold anymore. And so there's no space between the water molecules at that temperature to add any more sodium chloride. So an unsaturated solution would be the point at which you can add it in and it just dissolves. So if I keep adding salt in and the salt dissolves, I'm an unsaturated solution. You only get to the point of saturation where if you add more, it can't hold it. It's not max. So for example, here, this is, if you had 36 grams of salt at this temperature and 100 grams of water, that's totally saturated. If I had 26 grams of salt, it would be unsaturated. And if I somehow was able to get 40 grams of salt in 100 grams of water, then it would be super saturated if I cooled it to this temperature. So super saturated solution is kind of cool. You can play around with a super saturated solution if you've ever gotten they use them for like hot hands, not the ones you shake that have the iron filings in them. That's a exothermic reaction of iron. But the reversible hot hands, I'm not sure if you've ever encountered these, but they're like kind of this, they're kind of clear and colorless at first. And then there's a little button inside and you press the button and it hardens and releases heat. That's a supersaturated solution, typically of sodium acetate, which is the same stuff they put on salt and vinegar chips to make it taste like acetic acid. So acetate is that the vinegary taste. They put sodium acetate, the same stuff in the little hand warmers. It's on your potato chips. So if you cut open a hand warmer actually and you were to get it on your hands would smell like vinegar. Not that I haven't played with those before and cut them open, I have. So if you take these hand warmers and you press this little button inside and it turns from liquid into solid, and it's kind of cool. It kind of crystallizes out. It like from where the button is, it kind of goes out like this. I can just probably find it. So sodium acetate hand warmer. Because not everybody knows what I'm talking about. You can also make one on your own, but oops, I'll show you a video. It's kind of important to see it because you can understand what supersaturated solutions are. Okay. I hope that this is, okay, so this is the hand warmer. Let's see. Ooh, I do not want sound. Okay, it's too loud. So they're pressing the little button and you see how it kind of solidifies from the button. So it's releasing energy right now. So the process of the liquid turning to solid is exothermic. And then what you do after that is you put it in boiling water and the energy goes back in endothermic and it turns it back into liquid again. So what you're doing is you have a supersaturated solution of sodium acetate in there, and the inside of that container is so smooth that the solid doesn't have anywhere to like latch onto. It can't make a crystal. So to make a crystal, you need to like a place to like grab. So if you ever made, what is it? The sugar on the stick, rock candy. If you ever made rock candy when you were a kid or whatever, you know, you put the sticks in, you heat up some sugar in water, and then you put these sticks down in your sugar water and let it cool really slowly. And you crystallize the sugar onto the sticks. So that's what you need to have, some kind of something in the water. As it cools, the sugar has a place to crystallize. So with these hot hand warmers, the inside of the container is so smooth, the crystals don't have anywhere to grab to crystallize. And when you press that button, you kind of agitate it a little bit and shake it up a little bit, and it gets the crystals a little bit of energy and they start crystallizing, and then they kind of expand out from that. And that process is exothermic. So we use that solution, that supersaturated solution, for hand warmers. And then if I want to reset it, I put energy back in and it turns it back into a liquid again. But how do I make that solution? Yeah, so it's the same thing. It's just sodium acetate, liquid, turning into sodium acetate, solid. That's it. And it's exothermic, so the heat would be on the product side. And so to reverse that reaction, it's reversible. You would just add the heat back in and it would turn it back into a liquid. To make that, what you have to do is you have to, okay, so it's kind of hard to do. So you'll do this in some of your future labs. Hopefully you'll be back in the real lab and you can do this. It's kind of cool. We used to make sodium acetate towers. So you take one of those hot hands, if you order one from Amazon or whatever, and you cut it while it's liquid, okay, and pour it out. You can actually pour it out into a tower, because as it comes into contact with any sort of like place to crystallize, it will crystallize. And so it kind of, you pour the liquid out and it solidifies as it touches other solid. And so you can make, like, we used to do competitions in our lab of like who could make the tallest tower from the sodium acetate solution. But to make that solution, you take sodium acetate and you put it in water at its normal temperature. And then you heat it up and get all of that sodium acetate into the water that it didn't dissolve, and now we heat it up so the particles move, the water particles are moving faster, makes more space. So the water expands, makes more space for the sodium acetate. Then you cool it really slowly. And this is the hardest part, because if you take your test tube or something and you shake it up, it's going to mess it up. You have to cool it really slowly. You don't agitate it. You don't walk past somebody's table and accidentally bump it or anything, because they'll get mad at you. You very coolly let it go. So first you let it go to room temperature, and then you put it in ice or something. You very, very slowly cool it down. Then you have this super saturated solution. So what it is that you put too much stuff in the water, and now you're cooling it down, so you're shrinking the space between the water molecules. But because it was all originally dissolved, it's going to hold on to this dissolving. So the thermodynamics of it are a little bit beyond our class, but it's going to hold on to that essentially until it gets jostled, and it's going to let it go. So I want you to imagine this, that you're walking back from the car with groceries, okay? And if you're saturated, you're carrying as many bags of groceries as you can on a normal day. And if somebody tries to hand you an extra bag, you say, no, I can't hold that. I'm saturated with bags. If you're unsaturated, if somebody hands you an extra bag, you go, cool, I can take this extra bag, and you can walk into your home. If you're super saturated, that's on that day where you're like, man, I really don't want to make 2 trips to the car, and I'm pretty sure that I can take this pinky finger and hold this really heavy bag. And you are like stacking the grocery bags on top of each other. You know, it is very precarious. Any little thing is going to cause the whole system to collapse. Okay, that's super saturated. It's a very delicate situation. So much so that one press of that little button ruins everything. So that's kind of how we can use that. So think of an idea to help you get that. For me, my great-grandmother used to make sweet tea in the South. You add sugar to your tea when it's hot. And she didn't know she was making a super saturated solution. If you told her she was doing chemistry, she would tell you to get out of her house, because that's the devil's magic. Okay. That's how Southern I am. But she was doing a super saturated solution. She would heat up the sugar in the water on the stove, and then she would cool it to room temperature first, and then she would put it in the refrigerator in the pitcher. And if you mess with her tea, all that sugar is just going to fall out the bottom. But right before you would like mess with it, it would be so sweet that as a kid I loved it. But as I grew up, I was like, man, Nana, this is way too sweet. But if you're just gonna, it's a very slow process. You'll do it later in a lab, hopefully. If you can get back into a lab, you'll for sure do it. It's fun. But if you won't want to wait, order yourself some of those hot hands and cut open the edge. It makes a mess, so make sure you don't like aluminum foil or something. But if you cut open the side of it and pour it out, you'll find yourself making these like cool towers of super saturated stuff. But wash your hands afterwards, because you're gonna smell like vinegar. And don't eat it, even though it tastes like what goes on salt and vinegar chips. I don't trust it, because it's not made for food, so not FDA approved. So we talked about electrolytes before. Y'all know all about electrolytes. Here's some more with the pictures of electrolytes. If you dissociate into ions, you're an electrolyte. If you dissolve into molecules, you're not an electrolyte. Here's a solubility temperature chart. So you can kind of see that as we increase our temperature, we get more soluble, right? This makes sense. So if I heat my water up, I can dissolve way more stuff. Check out sodium chloride though. Like, you really don't, like I said, the sodium chloride is not as soluble as we think it is. You really don't get much more out of it. So you can like put salt in hot water, and it's really not going to dissolve that much more salt than if it was in cold water. It's just not. But with like calcium chloride, oh yeah, you get a lot more out of that one, right? Because it's a more exponential curve. This is for solids. Notice that all of these compounds are ionic compounds, and they're solids in water. Take a look at this though. Which cup, left or right, is cold? See if you can tell. Which cup has cold soda? Ooh, a battle, right or left? Ooh. Y'all are split. How many of you actually drink soda? Some people don't drink a lot of soda, so you're like, I don't know. So the cooler soda, and this is Coke, y'all. You see that red right there? That's Coca-Cola. Sweet Dixie champagne. My husband likes Pepsi, and that is not allowed in our household because we're from Atlanta, which is Coca-Cola world. Literally, there's World of Coke in Atlanta. It's where Coke was created and founded. I don't like Pepsi. I think it's too sweet. My husband likes Pepsi more, so we definitely fight about it. It's a miracle that we're even together. A Coke, it's like a rom-com. A Coke drinker and a Pepsi drinker, like, can't even get along. I went to Emory University, which is called Coca-Cola University. We're not allowed to have any Pepsi products on campus that were sold at all. Yeah, opposites attract. Yeah, chemist and biologist. Yeah. Dr. Pepper is real good. I like Mr. Pibb and Dr. Pepper both, probably the same, but Pepsi definitely. No mullets and no Pepsi. So this one is colder. I can tell, because look at all that extra gas. More CO2, more bubbles. Now, when we're talking about solids, okay, in water, if you increase the temperature, more of it dissolves. But if I'm talking about gas, if I increase the temperature, less dissolves. Increase temperature, less dissolves. So that lowers the solubility. So this is hotter because less bubbles. Less bubbles than that one. It's flat. Okay, let's think about it. Moving back up here, and I'll go back to the next slide. Does everybody get why increasing the temperature allows you to put more solid in? So you can think about your water molecules, the liquids moving around. If I increase the temperature, they're moving faster. They create more space. So water is less dense at higher temperatures because there's more space. If you have more space, you can fit more stuff in the space, right? Cool. Why, if I constrict it, do I keep more carbon dioxide? What's the difference between the compounds in the chart I just showed you and carbon dioxide? One is a solid, one is a gas. What's another difference between these compounds up here and CO2? So yeah, it's covalent. But there's some stuff covalent that dissolves fine. Sugar, for example, is covalent, and you can fit more sugar in water when it's hot. Not quite. This is CO2 aqueous. Let's just think about this. So solid sugar is covalent. It dissolves better in hot. Okay, solid sugar dissolves better in hot water. But covalent, this covalent gas, so the gas part is definitely a reason. And we'll talk about that in just a second. But there's another reason why CO2 doesn't like water. I'm using the word like as a hint here. Is anybody catching on? I'm not sure. CO2 doesn't like. Does like dissolves like, Liz? What does that mean? Like dissolves like. How do we use that in this context? Why doesn't CO2 like water? So it's a gas, so it's not like water because it's not a liquid. But you can get a solid to dissolve in a liquid. There we go. Water is polar, CO2 is nonpolar. So first of all, CO2 is a gas, okay? Also, it's nonpolar. So it like really doesn't like water, y'all. When we carbonate beverages, what do we have to do to carbonate a beverage? Have you ever use one of those like soda streams or something. Like, how do you get the carbon dioxide into the water? There's a special, like, something that we have to do to like get it in there. Yeah, so the CO2 really likes the other CO2s, and the water really likes the other waters, right? They don't like each other. So what you have to do, if you've never used like a soda stream or like one of those little CO2 canisters, you have to pressurize it, like a lot of pressure. You have to put a lot of CO2 and really pressurize it before the gas will dissolve. So you have to do two things to make a gas dissolve in a liquid, especially a non-polar gas dissolve in a polar liquid. First, we have to pressurize it. Okay, so this is showing the higher pressure. By pressurizing it, you're not letting the gas inside the liquid escape. So all of these gas particles, they're trying to get out. They don't want to be trapped in this water because they want to be flying around, moving around. Yeah. So if you just leave your cup of Coke sitting out, it's going to get flat because all the CO2 is trying to leave. It's not trying to stay there because gases want to be free. They want to be flowing around. I don't like being in this polar solvent, and I'm trying to be out there messing around with all the other gas. So you're trapping this gas in here. So we have to pressurize it, which is why you should always close your whipped cream at Starbucks. Yeah, so you put that CO2 canister in there, you're pressurizing, adding that CO2 to the cream to make it whipped. And if you run out of the CO2 canister, right, your whipped cream is not going to come out nice and whipped. It's just going to be like wet cream, right? So we have to pressurize it, and then the temperature. What is the temperature doing to this gas? The gas's goal is to escape. What is colder doing, Henry, to the gas particles? Or anybody? What is the colder doing? Think about how the particles are moving. Yeah, about slowing them down. So it's kind of vindictive. We're thinking about, how do we trap you? First, we're going to pressurize you so you can't get out. Then we're going to slow you down so you don't have enough energy to escape. Like, it's kind of, we're really trapping the CO2 in a place it doesn't want to be. Don't feel sorry for the carbon dioxide molecules because soda is delicious. If you like soda. If you don't like soda, then you can advocate for the carbon dioxide molecules to be released. But it's a little bit different than solids, okay? So gases and solids, solubility is different. So just remember that cold, pressurized is better for gases to dissolve, and hot is better for solids to dissolve. And you can just think about that, like with a can of carbonated beverage and a cup of hot tea. Like, those are the two examples that you need. Now, quick chemistry, real life pro tip. When you have a can of Coke, a Coke can, or we don't drink soda in our house anymore. We drink bubblies. They're like our little special treat. I know, we're old. Or LaCroix or whatever. Bubblies are the cheaper version of the LaCroix. But so all these carbon dioxide bubbles are homogenized throughout the can, okay? And if you really want to homogenize something, what would you do to it? If I really want to make something homogeneous, what would I do? What can I do? Let's say like I have some lemon juice in here and I really want to homogenize it. What can I do? Shake it up, right? Okay, so I'm gonna take my soda can, okay? I'm gonna shake up my soda can because I want my CO2 to be all homogenized. Are you cringing thinking about shaking a soda can? What happens when you shake it? It builds up pressure, yeah. So the CO2 is gonna try to escape when you open that soda can. If the CO2 is homogenized throughout the soda, the CO2 is gonna come out. And if the CO2 is at the bottom of the can, it's gonna bring the liquid with it when it comes out, which is why it's gonna spray everywhere. But if you jiggle the CO2, that's the technical term, if you jiggle the CO2 to the top of the can and then crack it open, no liquid will come out, only the excess gas will come out. So my friends used to make fun of me for tapping the side of the can over here to before I open my drinks, and then being like, that doesn't work. It does work. Coming from a chemist, it works. But it's better to tap the side of the can than it is the top of the can. You don't need the CO2 at the top of the can to be on the top more. They're already there. You need the bubbles at the bottom of the can to come up to the top. So you're going to tap the side of that can and kind of jiggle them to where they can kind of all come up to the top. when you release it, you won't have any issue. Yeah. So now you can explain to them why if you don't already know. And if you're getting made fun of for it, or if you're making fun of somebody for it, you better hush now, because now you know it does work. You have to, I mean, if you like shake your can real hard before you open it, you have to tap a lot before you get that done. But it does help to tap on the side of the can if you think that the can has been shaken recently, or you don't trust it to not be, you essentially, you are kind of flattening your drink, so it's not going to have quite as much CO2 in it, but you know, you're kind of getting some of that CO2 at the top just so it doesn't spray everywhere. If you shake the can and you tap the top after shaking, it will dislodge a little bit, but it really is only, you really want to get the CO2. It's not that the CO2 at the top that's the problem, because if it's at the top, it's not bringing a lot of liquid with it. It's the CO2 that's in the bottom that when it escapes, that when you decrease that pressure, because you're opening it up to the whole atmosphere, because it's like way higher than atmospheric pressure in that can. And when you open it up, it always flows high pressure to low pressure. So all that gas is going to flow out. If it's the bottom of the can, it's bringing all the liquid in between it and the top of the can out. That's why it explodes. Coke and Mentos is a different reaction. It's actually a gas evolution reaction between an acid and a base. And the Mentos have kind of a porous texture. So it gives the phosphoric acid a place to react. And so the Mentos has a basic something on the outside of it. I don't know exactly what compound it is. And the soda has phosphoric acid in it. And that's an acid-base reaction. It produces a gas. So it's a gas evolution reaction that does Mentos and Coke. Yeah. That's different than this. This is just a physical change, dissolving something as something else. Yeah. Learn something new all the time in chemistry class. All right, we're going to take a quick break. And then we're going to do some math. $5.13. Okay. One way in which we can determine measurements of solutions is through concentration. So concentration, probably should write it in a different color. It's a little too blue. So concentration is kind of like density. It's like how much stuff is in the solution. So it's a solute to solution relationship. And one way in which I can talk about concentration is through mass percent. It's the same mass percent that we were using to talk about oxygen and potassium chlorate for your mass percent lab. It's the same idea. It's part over the whole in mass. That's any percent. The part is the solute, and the whole is the solution. And the solution is the solute plus the solvent. So with any percent, part over whole, it's just that now it's going to be solute versus solution. So looking at this question, where am I? Get myself another page here to show you a little math. If I give you a percent by mass, and I want to know, well, how much carbon dioxide is in this much water? If it has this percent carbon dioxide by mass, I can turn the percent into a conversion factor. So just like we could use percentage, mass percents as conversion factors before, you could use them now. So if you want to go ahead and turn that percent, this percent right here, into a conversion factor, and see if you can figure it out. Now you can do it algebraically, or as you know, I'm going to show you how to do this with dimensional analysis, because I think that learning one type of way of solving problems is better than many different types. But you can totally do this algebraically as well. Most students just have trouble with algebra sometimes. I try to show you the non-algebra way, but see if you can get the amount of carbon dioxide here. Oh, you need one other thing. The density of water is on the back of your periodic tables. But I'll go ahead and give this to you. It's 1 gram per milliliter. And you use infinite sig figs here. At a certain temperature, that's the density of water. And it's just helpful to just kind of have that in your head. It's like, oh yeah, density of water is going to be 1 gram per mil. Let me know if you have an answer. You're gonna maybe private message the host version of me. The other version of me is not. Give you about 30 seconds to wrap up your work. So with this question, if you choose to do it algebraically, you do still have to do some converting first. So you have to do some conversions, then you can put it as algebra. So I prefer just to do it all as conversions. So I would highly recommend that we just take this percentage and turn it into a conversion factor. So if we just say that this is the percent of carbon dioxide in this solution from this lake, that means that 8.5, and I'm going to use grams for mass, that's easy, of carbon dioxide is equal to 100 grams of the solution. Okay, that's how we can turn this percent into a conversion here. The density is also another conversion, and the density is the mass of the solution equals 1 milliliter of the solution. So it's talking about the lake water. So solution here is lake water from this problem. You just write solution. You could also write S-L-O-N. It's an S. Sorry, I get a little excited with S's sometimes. S-L-O-N for solution. If you want to, that looks like S-D-N now. S-O-L-N. There we go. You can abbreviate that way if you want to. So I have some conversions there. And then I can see here that I have milliliters of solution, but they give me liters, so we need a conversion there. I'm going to use 1,000 milliliters as one solution. 1 liter. You can use 10 to the negative 3 liters as 1 milliliter, or you can use 10 to the positive 3 milliliters as 1 liter, whatever you have memorized. So if we start with 28.6 liters of solution, for every 1 liter of solution, I have 1,000 millis of solution. For every 1 mil of solution, I have 1 gram of solution. For every 100 grams of solution, I have 8.5 grams of carbon dioxide. And that's going to give me mass of carbon dioxide. So you should get 2,400 grams of CO2, or you can put that in scientific notation. We need 2 sig figs here because the 8.5. Either one. If you want to do this algebraically, I can show you how to do that. So answer there. So if I were going to solve this algebraically, it would be 8.5%, plug that in, is equal to grams of CO2, that's going to be our X, over your solution total. So that's going to be your 28.6 liters, but you have to change that to grams. So you have to do a conversion for that first. We'd have to do 28.6 liters. 1 liter is a milli. A milli is a gram. To do that first, so it would be 28,600 grams on the bottom here. So we would say, oh, times 100. First, you have to divide both sides by 100. 0.085 equals x over 28,600. Multiply both sides. And you get, oops, not 3. 2,400 equals x. That's how you could do it algebraically. If that's how you think about it, that's fine. For mass percent stuff, if y'all want to do it algebraically, just show me that work, right? Just like show it out. And you could even say like, okay, this is x grams, this is grams, so that I'm very clear on like what you're talking about. This is CO2, this is solution. You can label stuff in algebra. It's not the saying you can't tell me what type of substance you're talking about if you're doing something algebraically. So, you know, go for it. Questions about using mass percent here. It's the same as the way we used mass percent before. And you did a whole lab on mass percent. You did all those extra practice problems at the end about mass percent. So I'm assuming that we're probably good on this. So with any percent, you can always use it as a conversion, or you could probably do it algebraically. So with any kind of percent anything, you're probably going to have that same dilemma of, do I do this algebraically or as a conversion? I always suggest this intro, if you're struggling with the math stuff, that you turn your percentages into conversion factors and use it that way. But if you feel like algebra is a strong suit, then you want to do it algebraically, go for it. But for this question, you had to do some conversion first before you could do the algebra. So to me, it's just easier to do the conversions all the way through instead of switching between modes of math. Either way. That's just for mass percent. We're not done, because we can also tell concentration with moles. Yeah. So molarity is another form of concentration. Molarity is very similar to density, except for instead of grams, we're using moles. Molarity, like molitery, is moles per liter. Moles of solute over liters of solution. So moles are a way that we can tell amount of stuff in the solution. And that's what concentration is. So molarity is a concentration unit. Mass percent is another way to measure concentration. There are many ways to measure concentration. We're going to focus on mass percent and molarity, and that's it. There's something else called molality, which is little m. So make sure that you are doing uppercase m here, because little m is something different. Yeah, its hands are pretty gross. I think those are like mostly nails because they like dig through. I never looked at its hands before, but yep, moles are fun. The good news about these mole memes is that I don't have to make any of them. There are other people just as nerdy that make a lot of these mole memes themselves, so I just steal them. All right. And if you check this out, you would read this as per, right? That's a conversion factor. So we can say, if I give you number of molar, you can write that as number of moles of that thing equals 1 liter of that solution. So we can turn that. So if you're ever given some number and then an m after, turn it into a conversion factor. Don't let it stay. Here's the deal about molarity. It looks like 1 unit, but it's really 2 units. It's disguised. You have to take its mask off. Take it out of its disguise. Expose it like in Scooby-Doo, okay? Because it's gonna confuse you as to how to use it if you don't do that. You cannot use big M in dimensional analysis. You have to use mole and liter. So as soon as you see number big M, there's one special case in which you're not gonna do this, but every other time you see it, I want you to cross it out, and then I want you to turn it into a conversion like I just showed you here. So don't let it stay that way, just like we don't let Celsius live. We have to turn it to Kelvin. Don't let big M live. Turn it into mole equals 1 liter. Now, if I ask you for the molarity, then you need the moles, you need the liters. The same way if I ask you for molar mass, you need the mass and the moles. But if I give it to you, turn it to a conversion. The same way, like if you have molar mass, you should write it as a conversion, right? Same idea. So we're gonna say big M as the word molar. So 1 molar, okay, sodium chloride solution. So let's think about that. How would I prepare? If I said go in the lab and get me 1 liter of a 1 molar solution. Well, if I ask for 1 liter of a 1 molar solution, how many moles is that? It's going to be 1 mole over 1 liter, right? How many moles, sodium chloride, how many grams are in a mole of sodium chloride? The molar mass, right? So the molar mass can now be related to the molarity. So you would go and you'd weigh 58.44 grams of sodium chloride, and then you would add water until the 1 liter mark is reached. And this is important. If you add a liter of water, you might go over 1 liter total. So this is 1 liter total volume, because the sodium chloride itself may have some volume. So you would just add water until you get to a liter. So this is a cool flask called a volumetric flask, and it has one job. Its only job, it has 1 line. It doesn't make it less precise. Actually makes it more precise than like a graduated cylinder, because it only has that 1 line, means it only measures 1 thing. So the 1 thing it measures really well. It just measures 1 liter, that's all. So it doesn't measure half a liter, it doesn't measure 1/4 of a liter, it just has 1 job. So a 1 liter volumetric flask is more precise than a 1 liter graduated cylinder because it has 1 job. So it might have less markings, but it doesn't mean it's less precise. If you are a biology major, molarity, this whole section is going to be something you will use in any lab you go into as you move farther into science, into your biology degree. Chemistry for sure. I mean, yeah, this is like making solutions is how we do anything in lab. Everything you've used in lab or everything you've watched somebody use in lab on YouTube videos are solutions. They're not pure substances. They're all mixtures. Somebody in the stockroom has to do this to make those solutions for you. So if you ever want to get a stockroom job, which is good if you're a chemistry major to have on your like resume or whatever that you worked in the stockroom, or you just want a work study that's kind of cool, like you're going to be doing this. If you go into the biology lab, my husband's a geneticist. I hear him all the time talking to his colleagues about millimolar, meaning millimoles of solutions, concentrations of solutions that they're using to grow their cells in and stuff. All of this is something that you're going to use in any biological or chemical science that you go into. Physics depends on what kind of physics you're kind of getting into. If you're doing any sort of electrolyte solutions or anything like that, then you may use it. But if you're more into like the engineering side, you're probably not going to use too much molarity. But biology majors, chemistry majors, y'all are definitely going to need this. We're not going to do molality, no. not in this class. You will do molality, but just not yet. We're gonna do 2 types of concentrations in this class, mass percent, molarity. It's the same idea. I mean, any concentration is gonna be the same idea. Use it as a conversion factor. Like, do the math with it. But we're just not gonna introduce molality yet. They used to have molality in Chem 10, they took it out. They said it was a little too much. So next semester, you'll do some molality stuff. Let's try it. Let's see. What's the molarity if you have a solution of 15.5 grams of sodium chloride and you add water to make a 15-liter sodium chloride solution? I'm gonna give you about 2 minutes here. All right, so I got some answers here. So if I want molarity, I need 2 things. I need moles and I need liters. Which one of those things do they give me directly? They give me the liters. So what do I need? Moles. I need to know the moles. They give me the mass. So how can I find the moles? Molar mass, yeah. So we're gonna find the moles using molar mass. So work your way backwards for some of these is helpful, because if you kind of tell what you're looking for, what you have, what you need, that's just helpful. That's a helpful way of problem solving if you're kind of a little stuck. Working your way backwards is a good skill. So I get my moles here. And I'm just gonna leave this in the calculator. Like, I'm not even gonna, what's wrong? Not even gonna round it or anything. Oh, also one note about looking at your exams. Don't round molar masses. Always give me 2 digits out of the decimal or more. If you give more, the Canvas might mark you wrong, but I will go back and give you points. But if you don't put that, I do need to see at least 2 digits out of the decimal for molar masses. So don't be skimping the molar masses out. This is your moles. We're gonna now divide it by the liters that we have. So moles per liter. Whoops, not what I wanted, thank you. Moles per liter, that is molarity. So take this, just left at my calculator, divide it by 1.5, and you get 0.177. The unit is big M, and the substance is NaCl. So that's how you would write it. And you would read 0.177 molar sodium chloride. Got it? That's like just the basics of how to find molarity, okay? How to use it is sometimes a little harder for students. The key to using it, if I give you molarity, is to unmask it, okay? Is to not let it stay M. You have to rewrite it as a conversion factor. So all the times I've been yelling at y'all about do it in dimensional analysis, write conversion factors, it's because I can see the future. And I know that if you can do conversion factors really well, then new stuff like this is not gonna bother you. You're gonna be like, you know what? If I can make a conversion, I got this. So if you're still struggling with conversion factors, finding them, making them, putting them together, and you're really focused on like just kind of the numbers, and you're not really focused on the units and the substances, then you really need to focus in on ignoring the numbers for a while. Like, don't even write the numbers in your math. Just put unit and substances and see if you can set it up without any numbers, because it's the most important part of the way you're setting up this stuff. The numbers don't really matter very much. It's the setup. It's how you're thinking about it. Because you're really going to struggle in Chem 11 if you're not very comfortable with conversion factors. That should be a place of comfort where like, oh, if my professor gives me a conversion question, I can do it. You should be looking for those questions. All right, let's try it. Let's try, if I give you the molarity, can you figure something out with it? So how many grams of sucrose, there's your sucrose, are contained in 1.72 liters of a 0.758 molar sucrose solution? So I'll give you 2 minutes. Okay, so I've got some answers coming in. Let's see. I want to know how many grams of sucrose. So if I see that, I can go, well, I probably need the molar mass. If you just kind of have those habits from previous problem solving, then go for it. Probably need molar mass if they ask me or give me grams, and I'm going to go find the molar mass of this big molecule. C looks like a fancy E. All right, they give me 1.72 liters. All right, that's probably where I'm going to start because it doesn't really seem to have anything to go with it. But look at that molarity. Ugh, isn't it disgusting how it's just parading around as 1 unit, but really it's 2 units? Faker. Mole of sucrose equals 1 liter of solution. Unmask that molarity. It is so much easier to see what to do if you can see the mole and the liter. Promise, promise, promise. So get rid of that big M. Nobody likes a faker. Ooh, look at me, I'm just 1 unit. Nope, you're not, you're 2 units. At least molar mass is gram per mole, right? Molar mass is not trying to be 1 unit. Well, I guess AMU is 1 unit, but that's a different thing. A little bit different, same number, but okay, there we go. And if I'm gonna start with 1.72 liters of solution, I can use my molarity to find moles. When in doubt, mole it out. Just find the moles. Once you find your moles, hopefully your brain will catch up with what you are doing and you can move forward. 1 mole of sucrose is equal to 342.34. Isn't dimensional analysis beautiful? I can solve anything. Like reading Rainbow, I can do anything if I can find these conversions. I think it's just great. I get excited to like solve problems that I don't know. So whenever I teach a new class, I get like a new textbook, I get real excited to like go through and like solve new problems. I guess that just makes me like a big nerd, but it's all right. 22:11. There we go. If you got 447, I would guess it's probably your molar mass. Might be a little bit different than mine because you use more or less sig figs depending on what periodic table you're looking at. My periodic table is in my head, so yeah. All right, y'all figured it out? That's how you use molarity. Don't let it get any more complicated than this in your head, okay? It's gonna get more complicated because it's gonna be more steps. But just remember that molarity is just like molar mass. Did you finally, you probably, when you first started looking at molar mass questions, you were like, how do I ever learn this? And now you're probably very comfortable with it. Molarity is the same idea. It's just a conversion. Every time you see, except Nina, I'm gonna give you one special case where the molarity gets to stay big M. There's gonna be one special case. Every other time, if I give you a number and big M, you should turn it into number of mole equals 1 liter. Yep. Most of the time. Yep. There's going to be one situation where we don't have to do that extra work. So you know how like in gas laws, if you're at STP, 1 mole is equal to 22.4 liters. And it's like a shortcut around Pivnert, around ideal gas law. That's a special situation in which you can use a shortcut. For concentration math, we have a special situation where we can use a shortcut. I'm going to tell you what that is in a minute, but most of the time, you're going to want to turn it into the conversions and you're going to do all the math, okay? So now you can kind of see where I'm going with this. If I can use volume, liters, and molarity to find moles, what else can I do with moles? I can do anything with moles. I can use mole ratios in a chemical reaction. I can find mass using molar mass. If I have gas, I can put it into a Pivnert and find all kinds of stuff. So like molarity is just another way to get to moles. And moles is your central unit in chemistry where you can kind of go anywhere once you have moles. When in doubt, mole it out. If you're not sure what to do, find the moles and then go from there. All right. Here's another example. So So sometimes we want to know the concentration of a part of a substance. This is an example of leading up to something called equivalence. We're not going to learn about equivalence here, but if you're going into healthcare, you will learn about equivalence, because if you measure a patient's electrolyte levels, the report that you're going to get back from the laboratory is going to be in milliequivalents per liter. And it's telling you how much charge that you're getting from that electrolyte per liter of that solution. So equivalents are kind of moles of charge that you get for an ion. So sometimes I want to know the concentration of an ion specifically inside of a whole solution. So here's an example of that. Now, we're not going to get into the equivalent stuff in this class, but if you are in healthcare or nursing especially, and you move forward in your classes, you will run into that. And it is very similar kind of in math to this question here, or this will be a part of the question. So I'm going to give you a couple minutes to think about this. You need a mole ratio for this question. All right. I got some answers coming in, so let's give this a shot. So if I want molar concentration, what that means is I just want to know what's the molarity. So I'm trying to find the molarity of two different things. You're going to have two answers here. We want to know what is the molarity of the sodium ions and what is the molarity of the phosphate ions. And we're starting with 1.50 molar sodium phosphate solution. Okay, kind of just written everything out so I can put it all down here for you. So we can break this down. This is really moles over liters. And I even do this with the unknowns because it's just helpful for me to see that, right? That I'm really looking for moles and I'm looking for liters. And then this is really moles per liter. So 1.50 mole of, and always put your substance, because if you remember that when you have moles, we can have mole ratio and we can be changing substances, equals 1 liter, and we can just say solution. Now this liter of solution equal to all solution. And this liter of solution is all the same. And I know that the solution amount is not changing because it just tells me like, hey, inside this solution, what's going on? So we're not going to have to actually get rid of the liters of solution here. We want to keep the liters of solution. So what I mean by that is that this liter of solution is the same as this liter of solution is the same as this liter of solution. So when I'm setting up my dimensional analysis, I'm not ever going to want to cancel liters of solution. But you see here, I don't actually have something that's not a conversion factor to start with. So I'm going to have to start with the molarity, which is really the only thing that I have. And I'm going to separate it into two pieces, moles and liters. Okay? Don't write this, because that is not true. That molarity is tricking you into thinking that it's 1 unit. It got you. It tricked you. Don't let it trick you. It's 2 units. Break it apart every time. Except for my special case, which I haven't even told you yet, so get excited. There is a special case, so you don't have to do all that work. Now, for every 1 mole of sodium phosphate, how many moles of sodium ions are there? How many sodiums are there? 3. There's 3 sodiums in there, right? So multiply by 3. Mole per liter, which really means molarity. So we can say 4.5 molar sodium ions here. Yeah, if you just want to real quick, just take that, multiply by the number of things. For a multiple choice question where I'm not asking you to show work, just take that number and multiply it. But if I want to show work, show me a mole ratio, please. Thank you. 1.50 mole of sodium phosphate. Yeah, so I just had a student tell me that they're learning this in their nursing math class right now. They're probably learning equivalents with it as well, not just mole conversions, but actual like putting the charge equivalent on as well, which makes it a little more complicated. but it's very similar in how we solve it. Oh, I probably need to keep that 3 sig figs, huh? Phosphate. Watch your sig figs. I've been pretty lax about sig figs on exams because the way the Canvas has you enter it in, it doesn't do sig figs. So I'll check sometimes, like I'll pick one question per exam to like really check your work for sig figs, but most of the time, if you put it in the Canvas right, I'll just mark it right. Questions about this one? Where? Oh, because there's 1 phosphate. This is 1 phosphate, not 4. 4 phosphates would be like that. This goes all the way back to knowing those polyatomic ions. Yep. Yep. But this is the same way we break complete ionic equations down. Y'all remember that? Where we take the aqueous stuff, we break it apart. It's the exact same way you break apart ionic compounds for like these mole conversions. It's the same way you break it apart for molecular, complete, and net ionic. Yeah, so all of this is just, okay, if I have 1 liter of solution, okay, and this is same as my sodium phosphate. Inside this concentration of sodium phosphate, inside, not changing anything about the solution at all. I just want to measure, based on the molarity that's a sticker on the bottle, how many moles of sodium concentration is it? How many moles of phosphate concentration is it? But it's still, I'm not actually doing any sort of reaction or anything. I'm just telling you information about an existing volume of solution. So inside of that 1 liter, there's 4.5 moles of sodium and there's 1.5 moles of phosphate, because every time you have 1 mole of sodium phosphate, it breaks into 3 sodiums and 1 phosphate. So you're going to have more sodium ions per sodium phosphate, if that makes sense. Yeah. Cool? Are you ready for the shortcut? The fun equation that you only get to use sometimes. Yes. Yes, Liz. So if I give you kind of any sort of ionic anything and you need to break ions apart, you want to think about it like that, okay? How many of this ion, how many of that ion, based on the formula. Okay, there's a special equation. And I'm prefacing this because my biggest pet peeve, and you haven't even discovered my biggest pet peeve yet, is this. Is that students use this special equation because it's easy for everything. So I'm prefacing this with, this is very special what I'm about to show you, okay? We're going down into the like wine cellar for the real special vintage of wine that we don't drink every day, okay? Most of the time, when you are doing any sort of concentration math, you need to take your molarity, break it apart, and you probably need to use a mole ratio, okay? Because you're dealing with either a reaction or you're dealing with something like this equation where I have to relate part of a substance, okay? This next equation that I'm going to give you is special because it is only for one type of thing that you would do. And I call this my ice cream equation, because ice cream is something that I don't have a wine cellar, okay? I live in a tiny apartment. So, but I do have ice cream. So ice cream is my special thing that I only let myself have every now and then, again, because if I eat it every day, I won't be able to maintain my figure, right? So think about something for you that's very special that you only let yourself have some of the time, or something you buy, ice cream, something you eat, something you do for recreation, whatever. Something that you do that's special, that you don't do all the time, but that you only do some of the time for special occasions, okay? You don't have to say it out loud or type it in, just think in your head. That's what I want you to call this next equation. And if you just want to use this, the ice cream equation, that's fine. That's what I'm going to call it, because it's my ice cream equation. This equation is for dilutions, okay? Dilution means that I'm taking something more concentrated and adding water to it, and it's becoming more dilute or less concentrated. A serial dilution means that we're doing this in steps. So here's a picture of a serial dilution. So essentially what you're doing is you're taking a little bit of this cereal and you're putting it in this bowl with a lot of milk. So this one is more concentrated and this one is less concentrated. We call it more dilute, right? So we get going more dilute as we move down. So take a piece of this and then we put it in the new container. So if this molarity is like, say this is like 10 molar, this would be like 3 molar, and this would be like 0.5 molar, okay? So you're, by increasing the amount of water, or in this case milk, you're making it more dilute. You're not really changing necessarily, like this serial dilution is changing the number of moles in the solution, keeping the number of like volume the same. Each bowl has the same amount of milk. You're putting less moles in each bowl. But most of the time, we're just going to be keeping the same number of moles, but adding water. So in a lot of cases, it would look like this. It would be a container, and you would have, oh, this is your 10 molar. And then you would add some water, plus water, and you get a container that's got this much water, and now this is 5 molar. Does that make sense? So like the same number of moles are in there. I didn't add any more substance, the same number of moles still floating around, but now there's more water. So when you do the mole per liter math, the liter bottom is the bigger, so the molarity is less. Okay, so if you have mole per liter and you increase the liters, the molarity is going to decrease. Just fractional relationships, right? Keeping the mole the same. Increasing the liters is going to decrease the molarity. This equation can be written in two ways. You're going to see it if you're in nursing math class. You're going to see it as C1V1 equals C2V2 as well, where C is just equal to concentration. So any concentration, including molarity, you can use in this equation. You could use mass percent. If you're in nursing math, you may have mass volume percent, mass percent, volume percent, whatever. You can use any of those concentration percentages in this equation. We just usually use molarity, so I say M1V1, M2V2, but you can say C1V1, C2V2 as any concentration. Especially if you're going to nursing, you may want to just kind of think about it as the C equation. It's fine. Only for dilutions, okay? Only for dilutions. How can I tell I'm doing a dilution and not doing something else where I need to break the molarity apart? If it's the same substance before and after. Okay. I cannot use it for this reaction because sodium and sodium phosphate, they're different things. If I have two different substances, I need a mole ratio. I can use the dilution equation if I'm not changing substances, so I don't need a mole ratio. No mole ratio. You don't need a mole ratio here. Now here's the worst part about this and why I try to preface it with a warning. If you go to Khan Academy and you look up how to do molarity calculations, they use M1V1 for reactions, and you should never do that. So don't trust everything you find on the internet. That's why I preview videos and put them on Canvas for you, because I've watched them and I know that they're good. The students get real caught up on this and try to use this M1V1 all the time. You cannot eat ice cream all the time for every meal. You gotta have something else. This is your special, only open on special occasions equation. Never for reactions. Now you may have you may get to the point where you're doing a real complicated problem and you have some stuff you use, you do reaction math and then you do dilutions or something, that's fine. But if you're just looking at a chemical reaction and it's a seemingly simple problem, you should not use this. I will actually make it to where if you do use this, you're going to get the wrong answer. And if I see your work does this, I'm not going to give you any partial credit. I hate it. This equation, you get sick of it if you use it too much, and I'm sick of it. This is only special occasion. So this is like the ice cream that I will only eat on special occasions because I actually can't handle too much of it. It's real rich, okay? I discriminate against this equation. It gets used way too often. It's that song you hear on the radio. It's a good song, but you hear it too often. That's how it is to me when I just see it so often. My students write it down. So to be very clear, if you get the wrong answer because you use this equation when you should not have, I will not give you any partial credit because your work is wrong because you use this equation. So when in doubt, don't use this equation unless you are sure that you can use it. The ways in which you can be sure you're going to use this equation is if you see there's no reaction happening and you have the same substance and you don't think you need a mole ratio. If you use this equation for a reaction, okay, like I'm about to show you a reaction in a second. If you use this equation for a reaction and you get it wrong, I will not offer any partial credit if I see this work on your paper. So if I see you just pulling out M1V1 all the time, you're not going to get any partial credit for the questions you get wrong. If you get lucky, then I'll probably just let you have the points, but I don't want to see it. Is there a way to use it with mole ratio? Yes, but just don't. Just only use it for dilutions. Promise. Only when will only when you're doing a dilution, when you're not doing a reaction, when you have the same substance, and when you don't need a mole ratio. So up here, these are the conditions. When can you use this equation? Never for reactions. When you have the same substance, okay? No mole ratio is needed. Only for dilutions. Only in special occasions will you use this. You will not use this a lot. It's only going to be like 1 or 2 questions out of the whole exam. Maybe you'll have this, okay? When y'all get back into the lab, you need to remember, add acid to water, not water to acid. We always want to go aw and not wah. Okay? I'm trying to make it look like your eyes are like, yeah, okay, whatever. Because your beaker will explode, pretty much. It gets too hot. So when you go back into the real lab and you remember what I'm trying to teach you about lab in this class, it's always aw, not wah. Will you have to use mole ratio? So you have to do like what we did here. See how we use molarity and then we use the mole ratio? That's what I'll need to see. Not M1V1. So here's an example when you can use M1V1. So I'm just going to show you really quick because we're running out of time. You can definitely go back and kind of rework these with a little more time if you want to. So here's an example when I can use M1V1, because see how this is the same substance before and after, right? Same substance, check, okay. It doesn't have the word dilution in it, but I can kind of tell from the same substance, and I am diluting it. Am I diluting? That means, am I making it less concentration? Yes, because I'm going from 12 to 1.5 molar. And I can just read the question. It says like, hey, if you start with 12 and you're going to go to 1.5, that's getting more dilute, right? That's a dilution. Do you need a reaction? No. So that's good. That means you can use this equation. What's the other one? Do you need a mole ratio? No, because you have the same substance, right? So kind of a checklist for yourself. Is it the same substance? Yes. Is it probably a dilution because I'm changing molarities? Yes. Does it need a reaction? Because it have any words in it at all that talk about reaction, neutralization, product, forming? No. So I can use M1V1. You're clear to go. So it's so easy. Watch this. Use your ones. It doesn't matter if you do it this way or not, but I like to say this is my stock solution. So this is my B4 or more concentrated. Usually more concentrated, not always. This is my new solution that I want. Well, this is my V2 because I want 5 liters. This is my M2 because I want 1.5 liters. And I'm going to start with M1. So what do I need to know? I need to know how much of the 12. So in real life, what this means is that you go to the stock room and you find you have 12 molar potassium chloride. But your lab says you need 1.5 molar potassium chloride. So you're not just going to add water to the stock solution because that would ruin all the stock. I want to keep we keep things, we store it at high concentration and we just take a little bit out. Like if you're cooking, right? Like, you know, you don't, if I need to mix sugar and water, I don't just pour water into the bag of sugar. I take the sugar out and I mix it in with the water I want. Same idea. So how much of this V1 do I take out and put into the new container that's 5 liters? And it's going to be 1.5 molar. So the question is, how much of the 12 do you take out? Let's do it. M1 equals 12. V1 equals, I don't know. Just use milliliters if you're not told. Also, it doesn't matter if you call this 2 and this 2, you'll get, it's the same math. So don't really be concerned too much about labeling the 1s and the 2s. Just make sure that these 2 go together. Do you see how these 2 go together? Because there's words that link them of A. That means that this number and this number, they have to have the same number, even if it's 1. It's fine. My M2 is 1.5 molarity, and my V2 is 5 liters. Oh, that's liters. So just make sure that they're the same. So you're going to check your units to make sure all your units are the same. You don't even have to turn molarity into moles per liter. Don't have to do it. Just check all units match. What I mean by that is like, do the volumes match? Do the molarities match? The concentrations match and the volumes match? Good to go. Solve. I'm going to rearrange this little equation so that it says this, just like we did with gas laws. And I'm going to plug it in. Isn't it so easy? It's great. Look at this. Your molar cancels out and you get liters in the end. Isn't that great? That's why this is the ice cream equation. It's because it's nice. It's easy. It's easy to eat a lot of ice cream. It's hard to put it away and not use it. So the question asks you, how do you make this, right? So in my container, I'm going to pour in 625 milliliters, or 0.625 liters. Okay, so here's my 0.625 liters. And right now, this is 12 molar. If I want the end to be 5 liters, and I want it overall to be 1.5 molar, how much water will I add? So if this is my original 12 molar, put in this amount to my empty container, how much water am I going to add? Because some questions, the kind of hardest we can get is asking you questions about how much water you add. Because you'll put this 0.625 as your answer and be done, because it is very easy. The difference, yeah. You're not going to add 5 liters because you already have some liters in there. This is all the water that you add. That's it. You're not adding any substances, right? You're just adding the water. So this is your volume of water. Volume, water added. And your VW is always equal to your V2 minus your V1. So your final change in water is equal to your V2 minus your V1, the difference. So that makes sense, right? How much water did I add? Well, 5 liters minus 0.625 liters. Well, I added the difference of that, 4.375 liters, right? So how would you tell somebody to make this solution? You would say, take 0.625 liters of 12, put it in a new container, and then add 4.375 liters of water to that container. Or you can say add until you get to 5. Right? So it's a little more like, you know, explaining what's going on and just like math. You'll find where a lot of the questions on this are just like, hey, what's the amount of 12 you need? And your answer is 0.625 and you're done. But I just really wanted to show you kind of the reality of this that you actually use is real every time you're in a lab working. So if I were to, like when I taught high school, there wasn't a stock room. I had to make all my solutions on my own. So I did this math every single time I did a lab for my students. I diluted the substances that we used. I'm not going to give them 17 molar acid to burn their faces off. So I have to dilute it every time. All right, it's 6:15. If you have to go. I am going to finish this last piece where we're going to come now out of the world of easy dilution math, okay? We're going to go into the world back of mole ratio. So wake up from your dream of ice cream and come back to the real world with some moles, okay? Let's do a quick check of this because I'm going to show you and you're going to see exactly why people want to use M1V1. Don't you see 2 M's? Don't you see it's asking you for a volume? And I can say how much in liters. Oh, 1 liter, 2 liter, 1 M, 2 M, M1V1, right? Let's do a quick check. Is it the same substance? No. One substance is sodium hydroxide, and the other substance is sulfuric acid. Neutralize is a key word. Does it say anywhere about dilution? No, it doesn't say that. Is it a reaction? Yes. How can I tell it's a reaction? The word neutralize. So therefore, you cannot, conclusion, cannot use M1V1. This is the first time I've taught it like this, so hopefully y'all will not make this mistake and this will work. Scaring you out of doing it in the beginning will hopefully help you make the mistake less. And it's going to help you because you're going to get better grades. Okay, cannot use M1V1, so don't even try. Yeah, so Michael said, hey, this is a reaction, right? So what do I need if I automatically see that I need a reaction? What do I need? Gotta write a chemical reaction. Sodium hydroxide reacts with sulfuric acid. What kind of reaction is this? I'm gonna let y'all write those products. Unless you type in what kind of reaction it is. Again, if y'all gotta go, you can go. It's past class time. I'm just gonna finish this video. What kind of reaction is it? Is it synthesis, combination, single replacement, double replacement, or combustion? We gotta do that final exam practice. Think about everything. Double replacement, yep. So my sodium is gonna hook up with my sulfate. And my hydrogen hooks up with my hydroxide. It makes water. There's your neutralization. You're making neutral water, yeah? You can put in aqueous for all these things if you want to, but you don't have to just to solve this question. Give me a little balance in here. There we go. Now we're balanced. Now, the way I like to do these is I like to write underneath the reaction everything that's given to me in the reaction because these questions, for some reason, with the molarity, students just get really confused. Like if I give you grams, you know how to use molar mass. But if I give you molarity, it's like, oh, I don't really know. Sometimes students get the volumes mixed up from the substances they're supposed to use. So I like to just keep everything right underneath the substance I'm talking about. So underneath the sodium hydroxide, I'm gonna write everything I know about sodium hydroxide. I know 0.125 molar goes with sodium hydroxide. Just let it stay for right now. And I wanna know how much sodium hydroxide. So I'm gonna say, well, I wanna know question mark liters of sodium hydroxide. What do I know about sulfuric acid? Well, I know it's 0.225 liters, and I know it's 175 molar. Okay, so that's what I know. And it's so helpful for me to write it like this. Now I can go back and I can really turn those molarities into conversions because I can't use M1V1. If you use the M1V1 here, you will get it wrong. It will not be the right answer. If you don't believe me, you could try it. Let's turn this. I can't handle this molarity pretending like it's 1 unit. What a faker. You're really moles of sodium hydroxide equals 1 liter of sodium hydroxide solution. Let's just say like this. And you don't have to use the aqueous when we're doing the math, but just so that your moles and your liters are of the same solution. They're of the same thing. Turn this molarity into a conversion. I can't handle you. Mole of sulfuric equals 1 liter of sulfuric solution. And again, I'm putting aqueous here to indicate solution. We can drop that aqueous when we do that math. Okay, I already know I need 2 different substances, right? Because I did that little M1V1 check. So what do you need if you have 2 substances that you're trying to do math with? What do we need? A mole ratio. 1 mole of sulfuric is equal to 2 mole of sodium hydroxide. Getting really excited with my S's here today. There we go. Gotta have a mole ratio. Now let's take a look at what we got. I want liters of sodium hydroxide. Okay, so here's liters of sodium hydroxide connected right here. Moles of sodium hydroxide. Moles of sodium hydroxide. So remember that we first started doing dimensional analysis. I want you to think about this, and I'm going to erase this in just a second. But you know, in those movies where they're trying to track a killer and they have like the bulletin board, all the strings attached, everything. That's kind of what we're doing with our units. So what I want connected to here, these moles of sodium hydroxide connected here. These are connected, right? Because everything is connected to each other. Moles are connected here. And these liters are connected to these liters. I can connect given information all the way to unknown information. So I'll get that again. I can take given information and go all the way to unknown information, given what I have written here. And that's kind of your goal. When you know you're done writing conversions is when you can connect everything. Sorry about the cooking sounds. My husband's cooking me dinner. Isn't that so nice? He's not mad at me about the Coke anymore. I've gotten past it. That's what marriage is. It's about compromise. I let him have his Pepsi and I don't judge him. So we're going to start with the thing we know the most about. Don't start with sodium hydroxide because they're asking you about sodium hydroxide. So you can't do anything with it. You don't know anything about it because they're asking you for it. I don't externally judge him. I just judge him on here. He can hear me, but sometimes he can't. Coke is a superior product. Okay, so 1 liter of sulfuric. Again, I'm starting with the sulfuric because I know the most about it. You start with what you know, and then you venture into the unknown. 0.175 moles of sulfuric acid. Now, this also is going to help you if you remember when in doubt, mole it out. Just find moles. Can I find moles of sodium hydroxide? Because I don't have the liters of sodium hydroxide. So, I mean, I can turn this into a conversion, but I can't find moles. Can I find moles of sulfuric? Yes. If you have liters and molarity, you got moles. Thank you, Jeremiah. Thanks for coming. The rest of this is on a recording, all right? Oops. So my 1 mole of sulfuric is equal to, this is the last little piece, y'all, and then we're done. So if you're barely hanging in there with me, I'm going to finish this. And if you want to watch the recording later, you totally can. Whoops, I went too far because I was talking. So what do I need? Oh, I need liters. Oh, okay, I'm fine, never mind. I'm good. We're going to keep going. Sometimes we'll stop there when we're trying to find the molarity because we're trying to find the moles. Let's make sure everything cancels out because this is a kind of a new problem. And notice that I put the substances here so I don't accidentally cancel a mole of one thing. Henry, because I have to start with the moles, or start with the substance I know the most about. Like what else is there on here that's not a conversion that I can start with, right? There's nothing else. I don't like to start with a conversion, so I can't start here. I don't want to start here. I don't want to start here. The only other number I have is this, which is why it's so important to turn your molarity into a conversion, because otherwise you'll just start with molarity and think that, you know, you can cancel that, which you can't. And a lot of times you won't be given your volume in liters, you'll be given milliliters. You just do a quick conversion and turn those milliliters into liters before you start. What'd you get? 0.630 liters of sodium hydroxide. I'm doing this on my iPhone calculator, so if I'm wrong, definitely tell me. So definitely it's not the most reliable. Cool. So work through the problem set. We're a little bit ahead of schedule. We're supposed to be doing 13 again on Tuesday, but I'm going to try to get us finished with all the chapters as soon as we can. And then if we have any extra days at the end, we'll spend that on full review for the final. So we'll start with chapter 14. All of them in the schedule, so we have more review days for the final. I think that's more helpful than, I think I'd rather just go a little over and then have more review days at the end. Great. Chapter 13 problem set is going to be something that you definitely